Okay, so in this one, whereas we tackled the notion of matrix multiplication in the last one, here I want to talk about the kind of idea behind matrix division. Now, people very rarely talk about matrix division in these kinds of terms. The way that we're going to frame it is by talking about something analogous to the number one in for the real numbers, but in the world of matrices, and then talk about what it means to take the reciprocal of a matrix, and that's going to be the concept of an inverse. And the way that we're going to think about matrix division is that dividing by a matrix is really the same thing as multiplying by its reciprocal, that is to say, its inverse. Okay, so hopefully all of this will make sense, but let's take a look here. So first of all, let's think about the following matrix, and I'll define it in the following way. The n by n identity matrix. This is what I'm going to define for you. The n by n identity matrix, which I think the textbook denotes either I sub n or just I. I sub n or just I if the number of rows and columns is clear, okay, is the n by n matrix whose ij entry is either 1 if I is equal to j and 0 if I is not equal to j. Now, this might be inscrutable at first, but this is saying something very simple, okay? It's saying that the entries, this is a square matrix, it's got n rows and n columns, and it's saying that when the column index is the same as the row index, that's when the entry is equal to 1. So what that's going to mean is the following. Let's just look at some examples here. And this is going to be very clear. For example, I1 is the 1 by 1 matrix. There's only one entry, and the row index is the same as the column index, so that entry is 1. That's I1. I sub 2 is a 2 by 2 matrix. It's looks like this. Okay? The places where the row index is equal to the column index are here and here. And those are precisely where the ones live. How about I sub 3? Well, that's 1, 0, 0, 0, 1, 0, 0, 0, 1. And I bet you can guess what I sub 4 is. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay? And etc. These entries in a square matrix where the row index is equal to the column index, sometimes called the main diagonal of the matrix, of any square matrix. And what the identity matrix is a matrix where the main diagonal is populated by ones and anything not on the main diagonal are populated by zeros. Okay? Why do we care about such matrices? We give it a special name. Why? Why do we care? It's because of the following fact. If A is any n by m matrix, then if we take in and multiply in on the left of A, then this, remember, this is n by n, and this here is n by m by assumption. So the product makes sense because the number of columns of in is equal to the number of rows of A. And what we get, in fact, is exactly A. This is the point. Is that the identity matrix, when we multiply any matrix by it, just gives us the matrix back. This is why the identity matrix is kind of analogous to the number 1 in the real numbers. It's because you take any real number like 8 and multiply it by 1, you get 8. You take 17, multiply it by 1, you get 17, right? If you take any matrix and multiply it by the appropriately sized identity matrix, you'll always just get the matrix back. Okay? Let's just see this in action. Oh, and similarly, I'll say, or maybe I'll just write and. If you take A and multiply by I sub M, right? You need a different identity matrix because potentially M and N are not the same. You still get A. Okay, so for example, let's say that we have the matrix 2, 3, 1, 0, 8, 4. And let's say this is our matrix A. Then I can examine the matrix I sub 2 times A. That is the 2 by 2 identity matrix, 1, 1, 0, 0. Sorry, that's the way I pronounce it in, I don't know what I'm doing. Times A, which is 2, 3, 1, 0, 8, 4. And we can compute this product because we know how to do matrix multiplication. We interleave this row with this column, this row with this column, this row with this column, doing dot products. And then to get my second row, like this. Okay? And what do I end up with when I do this? So I get 1 times 2, which is 2, plus 0 times 0, which is 2. And 1 times 3, which is 3, plus 0 times 8, which is 3. 1 times 1, plus 0 times 4, which is 1. Oh my god, it's the same. Huh. And then let's do the interleaving the dot product of this row with these 3 columns. The dot products. I believe I get 0, 8, 4. Okay. And I'll let you check that if you do A times A sub I sub 3. So in other words, if you do 2, 3, 1, 0, 8, 4, and you multiply this by 1, 0, 0, 0, 1, 0, 0, 0, 1, that you'll get precisely 2, 3, 1, 0, 8, 4. In other words, you'll get A back. Okay? That's the identity matrix. That's the point of it. Okay? And it's going to come in really useful, very useful to talk about this. All right? Maybe just some more terminology, so definition. If A is a square matrix, and I've already mentioned this, but let me just write it down. The main diagonal of A is the entries are the entries consist of the entries. Sorry, consist of the entries whose row index is equal to its column index. Okay. So all I'm saying is if you have a matrix like 1, 3, 5, 0, 2, 8, negative 1, pi, 7, then the main diagonal is simply these entries along here. Because the row index of this is 1, so is its column index, also 1. The row index of this is 2, its column index is also 2. And similarly, the row index of this is 3, and its column index is also 3. That's what I mean. Okay. Then we say that a matrix is diagonal. Square matrix is diagonal if the only non-zero entries, or let me say it like this, if the entries that are not on the diagonal are 0. If the entries not on the main diagonal are 0. So the identity matrix is what's called a diagonal matrix. Okay? And I'm going to say one more thing. Definition. A diagonal matrix is a scalar matrix. If all the entries on the main diagonal are equal. Okay, so something like 2, 2, 0, 0. Not only is it a diagonal matrix, but it's a scalar matrix. How much time have I spent? 10 minutes. Okay. Now, what do I want to say? So facts. Every scalar matrix looks like some lambda, some number lambda. I don't know why I'm choosing. Well, I do. Some number lambda times the identity matrix of the appropriate size. Do you believe? I mean, this makes sense, right? We're going to take this number, lambda, we're going to multiply every entry of the identity matrix by it, but that's going to give us a diagonal matrix whose diagonal entries are all equal to this number, lambda. Can you all see that with your brain? Okay. Now, why do we call these scalar matrices? It's because if you take lambda times I sub n, let's just assume that I has the right size, and we take any matrix A and multiply by lambda times the identity. Well, this follows from many other things that we've talked about, but this is going to be equal to just lambda times A. Okay? So it's just the result of multiplying any matrix by a scalar matrix is to just multiply that matrix by that scalar, which we're going to call lambda for reasons. Okay? All right. Let's see. Is there anything else that I really want to say? Oh, yes. Right. One other thing. And this has to do with matrix inverses. Okay? So if we have the thing that's analogous to 1, we now want the thing which is analogous to taking a reciprocal, so that we can define the notion of matrix division as multiplication by the reciprocal. Okay? So a matrix A has, or sorry, let me set this a little bit better. So suppose A is a square matrix. Square n by n matrix. Okay. Then sometimes, not always, sometimes you can find an inverse of A, which we denote A inverse. Now, I know that looks exactly like a -1, but everybody in the world pronounces that A inverse. With the property that when you take A and you multiply it by A inverse, you get the identity matrix of the appropriate size. And similarly, A inverse times A is also equal to the same identity matrix. Okay? This A inverse is what I kind of mean by the reciprocal of A. And multiplying by the reciprocal of A is what one could possibly mean by dividing by A. All right? Let's see an example of this. Of a matrix and its inverse. So let's take A to be the matrix 4, 3, 2, 2. Okay? So there's A. And now I claim that A inverse is going to be a matrix. It's going to be the matrix 1, negative 3 halves, negative 1, 2. Okay? So this is my claim. I'll just call it a claim. How can I check this claim? I can check this by doing the product A times A inverse. All right, so this is 4, 3, 2, 2 times 1, negative 3 halves, negative 1, 2. And what do I get here? So this row times this column, I get 4, 3, so that's 4 minus 3. I think I get 1 here. 4 times negative 3 halves. Oh my god. I think that's negative 12 halves. I think that's negative 6. Plus 3 times 2, which is 6. Oh my god, that's 0. 2 times 1 is 2, and 2 times negative 1 is negative 2, and you sum them, you get 0. And then 2 times negative 3 halves is negative 3 plus 4. I think negative 3 plus 4 is 1. Oh my god. This is the identity matrix is the point. Okay? And similarly, you can check A inverse times A is also equal to the identity. Check this yourself. Okay? Good. So what this shows is that this matrix, 1, negative 3 halves, negative 1, 2, really is the inverse of A, because when we multiply, when we form the product of A inverse with A, we get the identity matrix of the appropriate size. Okay? All right. So fact. If the matrix A inverse exists, and it doesn't always, if A inverse exists, because it doesn't always, then we say that A is invertible. Yeah. Not all matrices are invertible. Or even square ones. Let me give you an example. And we'll learn about a criterion next time. But let's take the matrix 2, 1, 1. Oh my god, what am I doing? 2, 1, 4, 2. Yeah, better. This is not invertible. Now this might be difficult to understand. Why? Why is it I can't multiply this matrix by something to give me the identity matrix? I claim you can't, and I'm right. But I can't tell you right now. I'll tell you in the next set of videos, okay? Another example. This one's easier to understand. What if I had the matrix 0, 0, 0, 0? This is not invertible. Because I don't think it's hard to understand that if you multiply any matrix by 0, 0, 0, 0, the zero matrix as they call it, you're going to get the zero matrix out. So you can never possibly get the identity matrix. You feel what I'm saying to you? You can't respond. But yeah, that's the idea. Okay? And it turns out even like examples like this, if you have like a 0 row, like if you have 5, 7, 0, 0, this is not invertible. Okay? I'll end with just one more fact. All right? Which is the following. If you take A inverse, okay, and you invert that, you know what you get? You get A. In other words, A is the inverse of A inverse. Think about that. A is the inverse of A inverse. Okay? All right. That's enough for this. Tomorrow, or in the next, not tomorrow, but in the next set of videos, we will talk about a criterion for deciding when a square matrix is invertible. That's going to be very important for us. It's called the determinant. Okay. And we'll get into what all of this is useful for. It's useful for so many things, but for us, the first thing that we're going to do is learn how to use matrices to solve linear systems of equations. Not unlike you might have learned, at some point in your high school career, but we're going to apply it to that problem. Okay, that's enough for now. So long.